In this one, we're going to find the equation of the straight line that best fits our paired sample data. If there is a linear relationship between the two variables, this equation will algebraically describe that relationship. This best fitting straight line is called a regression line, and its equation is called the regression equation. So the regression equation expresses a relationship between x, which we call the explanatory variable or the predictor variable or the independent variable, and y, which we can call the response variable or the dependent variable. The typical equation of a straight line, y equals mx plus b, is expressed in the form y hat equals b sub 0 plus b sub 1 x, where b sub 0 is the y-intercept of the line and b sub 1 is the slope of the line. So our regression equation, given a collection of paired data, the regression equation y hat equals b sub 0 plus b sub 1 x, algebraically describes the relationship between the two variables. And the line that is the graph of this equation is called the regression line. It's also called the line of best fit or the least squares line. And what this line does is it minimizes the sum of the squared errors or residuals. The errors or the residuals are the differences between the observed values and the predicted values of y. The requirements for this, first of all, the sample of paired data has to be a random sample and it has to be quantitative data. Second, visual examination of the scatter plot has to show that the points approximate a straight line pattern. Third, any outliers must be removed if they're known to be errors. If they're not known to be errors, then at least consider the effects of any outliers. Here's an example. If we use technology to find the equation of the regression line in our situation with the colas drunk per week and the bone mineral density, this is that same procedure in StatCrunch that we use to find the correlation coefficient. It also gives us our regression line. So our regression line is right here. So we would write this out as y hat equals 0.8861 minus 0.0029x. Notice that in StatCrunch, it gives you the names of the variables instead of x and y. So the one that's on this side of the equation is the x, the one that's on this side is the y hat. This will also give you the scatter plot with the regression line drawn in. So the line in red is the regression line. Earlier we did a hypothesis test that showed that there is a linear correlation between the two variables. So that means that we can actually use the regression line to predict bone mineral density given the number of colas drunk per week. Example, for a woman who drinks 9 colas per week, we would predict that her bone mineral density is this. Notice all we're doing is taking our regression equation and putting in 9 in place of the x. That turns out to be 0.86 grams per centimeter squared. So that would be her bone mineral density. For a woman who drinks 2 colas per week, our predicted bone mineral density would be 0.8803. Notice in this one we're plugging in 2 in place of the x. And if we look at the scatter plot and the line up here, for the woman who drinks 9 per week, that value would actually be over here where x is equal to 9, and our y value would be wherever our y value is on that line. For the 2, we're looking at the point on the line where x is 2. So the value we came out with, 0.8803, is the y value for this point right here. Now when we're trying to use our regression equation for predictions, we can only do this if, number 1, the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. In other words, we need to look at the scatter plot and the regression line. Also, if we conduct a hypothesis test for a linear correlation and it indicates that there is a linear correlation between the two variables, that's why we do the hypothesis test. And the third thing is that the data don't go too much beyond the scope of the available sample data. Predicting too far beyond the scope of the available sample data is called extrapolation, and it can result in bad predictions. Now, if we don't have these three conditions met, then that would mean that our regression equation is not a good model to predict our y values. So in that case, the best predicted value of y is just the mean of the y values. Okay, so here's a little flow chart for doing this. If we want to predict values of y, first we have to look at whether the regression equation is a good model. So here are the three questions that we have to answer. If the answer to all three of these is yes, then the regression equation is a good model, and all we do is substitute our value of x into our regression equation, and that gives us our value for y hat, our predicted value. If the answer to any of these is no, then our regression equation is not a good model, and in that case it doesn't matter what our x value is, because our best predicted value of y is just going to be the mean of the y values. So in this example of hospital charges and patient age, we determined that there was not a linear relationship between the two. In that case, if we wanted to predict hospital charges for an 80-year-old man, we would get the same answer as we would for a 20-year-old man, which would just be the average charge from our sample data. So the mean of our charges from our sample data was $7,647.36. So that would be our predicted charge for an 80-year-old patient or for any age patient.